Okay, so I now want to look at some properties of solutions to the diffusion equation, and we're going to give it an initial condition here. U of x0 is equal to f of x. Okay, so the solution is u of xt is equal to 1 over the square root of 4 pi t times the integral y going from 0 to infinity. I'm going to write it like, no, that's not how I'm going to write it, never mind. E to the minus x minus y squared over 4t dy. Now there's a few properties that I want to mention about this. Okay, the first thing that I want to do is observe. Actually, let me back up a little bit here. So this is called, this has many different names, but one of the things that this is called, it is the heat extension of F to the upper half plane, which I'm going to abbreviate as UHP. So this is it's called the heat extension of F to the upper half plane. And what it's doing is it says we have a function f that's initially takes in values, it's only defined on the real line, but this extends it up into the upper half plane. The upper half plane meaning we're going to look, this is the real line, it's the x-axis here, and then the t-axis goes up here. So it extends the function f up into this region here. And then think about its graph is coming out of the board here. So the graph of f along x is a graph coming out of the board here. And then for any fixed value of t, this function u of xt is going to be the temperature profile or whatever u is measuring at that value of t. And again, the graph is coming out this way. Okay, so it takes a function that's initially only defined on the real line and gives you a function that's defined on the whole real, or sorry, not the whole plane, but the upper half plane. That is for t greater than 0. So the definition of the upper half, well, okay, you know what it is. So there's several things to prove here. I'm not actually going to prove any of them, but I want you to think through why they might be proven. I'm going to give you an idea for why they might be true. So first of all, I just want to verify, like, does this actually solve the diffusion equation? So in other words, is the t derivative equal to the double x derivative? So to do this, verify that the function e to the minus x minus y squared over 4t divided by the square root of 4 pi t satisfies the diffusion equation. Okay, now if all of our logic and all of our things worked appropriately with Fourier transforms and stuff like that, it should satisfy the diffusion equation. That's kind of what we, how we did this. But let's just take this and verify whether or not it satisfies the diffusion equation. Well, the first step is we're going to verify that this satisfies the diffusion equation. And this is something called the heat kernel. And we want to show that it satisfies the diffusion equation for t greater than 0 and for all x values. So when t equals 0, there's a problem here. Okay, so we want to show that satisfies the diffusion equation for all x. Okay, the next thing that we want to do is we want to compute the t derivative of u. So we want to say that the t derivative of u, we want to put this derivative on the inside of the integral. We want to say that this, let me actually look at the double x derivative first. We want to show that the double x derivative of u, or no, let me go back to t, sorry. We want to show that this is equal to the integral y equals y equals minus infinity to positive infinity f of y times the t derivative of e to the minus x minus y squared over 4t divided by the square root of 4 pi t dy. We want to show that we can do that. In other words, the t derivative should be on the outside of the integral. We want to show we can pass it in. Now, the first thing that tells us we should be able to do this is that it is a y integration. The bounds don't depend on t. And so that's the sort of thing that first lets us naively put the t derivative on the inside. But to prove that we can do this in general, what we need to do is prove that there is a function of y. It can depend on y and x that is independent of t. We need to find a function independent of t such that that function is bigger than this derivative, and f of y times that function is going to be integrable. So look at Wikipedia, look up look up Leibniz's rule for exchanging integration with differentiation for a precise statement of when you can do this, and then prove when you can do this. And I don't prove this in the notes, but I prove a similar statement for the Laplace equation on the upper half plane that you can look at. There's a little trick that you have to do because there is no function that satisfies what I just said for all values of t, so you have to think a little bit about it, okay? And then similarly, what we want to show is with the x derivative, the double x derivative. Okay, but formally at least, since this satisfies the diffusion equation, u is also going to satisfy the diffusion equation. Since this satisfies the diffusion equation, u is also going to satisfy the diffusion equation. And I want you to think through why that is. In other words, allow yourself this luxury of interchanging the differentiation and the integration. And if this satisfies the diffusion equation, I want you to convince yourself that u then satisfies the diffusion equation. Okay. The next thing that I want to mention, and again, this is another thing that I did not prove this in the notes, but I want you to also show that the limit as t goes to 0 of u of xt is equal to f of x for all x. Now, I didn't prove this, but you can probably mimic the proof that I have for a similar statement in the Laplace equation section to prove this. Okay. Okay, the next thing that I want to show you, or the next thing that I want to talk about or make you aware of, is since e to the minus x minus y squared over 4t over the square root of 4 pi t is smooth for t greater than 0 and for all x. Smooth meaning it's infinitely differentiable. Okay, so it's smooth for all t greater than 0 and all x. Then so is u of xt. Now, this is an interesting fact. Why do I say this is interesting? Well, notice the differentiability properties of u have really nothing to do at all with the differentiability properties of f. So f can be as messed up as we can conceivably think of it being, and I'll give an example in just a moment. F can be very messed up, yet its heat extension is going to be smooth for all values of x and t. So the heat extension is called a smoothing operator. Solutions to the diffusion equation with f as the initial data are set to smooth f. Okay, it's a smoothing operator. You take a function that is very badly behaved in terms of differentiability. We do need it to be integrable, at least in some sense, but you can take f to be a very badly behaved function in terms of differentiable, and its heat extension is going to be infinitely smooth. That is, it's going to be smooth, that is infinitely differentiable for all t greater than 0 and all values of x. Okay, so now this is interesting because I can take a very rough function. It's not differentiable, not continuous. Maybe there's a huge singularity, which we'll see in just a minute. But for any value of t greater than 0 like t could be equal to 1/1,000,000th of a second or whatever, we're going to get a smooth function. So this is a very interesting property of the diffusion equation. And I want to look at it in a particular case. I want to look at a particular case of it. What if f of x is equal, what if f of x is equal to the Dirac delta mass at 0? So this is now going to be the Dirac delta. Let me write it in purple so you know that'll denote that I've made a change. Okay, so what is this integral equal to? Well, remember what the Dirac delta distribution does. It just evaluates the other part of the other function in the integral there at 0. That is where the variable y is equal to 0. So this is equal to e to the minus x squared over 4t divided by the square root of 4 pi t. So notice here, this gives us reason to believe that this is a solution to the diffusion equation, because in terms of Fourier transforms, this is, that the Fourier transform technique shows this is a solution to the diffusion equation. But I want you to actually to get your hands dirty and compute it. Okay, so notice what this is saying. So delta has a huge singularity. If we think about delta just sort of in terms of functions, it's so badly behaved it's not even a function, it's a distribution. But if we think about it as a function, there's a singularity at 0, it's infinite there, and 0 everywhere else. Of course, because that doesn't make sense in terms of a function, it's actually a distribution. But the point is, delta is so badly behaved, it's not even a function, yet its heat extension, or the solution to the diffusion equation with this as the initial data, gives us an infinitely smooth function, or an infinitely differentiable, i.e. a smooth function. The other thing to note here is notice that for all, if t is greater than 0, then u of xt is greater than 0 for all x. So imagine u is modeling like the concentration of dye. You have a infinitely long pipe of water or something, and you have an infinite concentration of dye at 0 at time t equals 0. Okay, what this says is that if you have that dye and let it go, like let it start to diffuse, what this says is that actually for any positive time, there's going to be there's going to be dye all along the pipe. Mathematically, that's saying what's happening here. Mathematically, that's what's happening here. Then we go from infinite concentration at time 0, and now for any positive time, there's going to be dye all along this infinite length pipe, or infinite length pipe. Well, physically, obviously, this can't happen because that would require dye traveling faster than the speed of light, of course. Mathematically, this is what happens, though, and it actually is capturing something about the diffusion equation, the fact that it's smoothing, that I'll mention in just a moment. Okay, so what this is called is infinite propagation speed of singularities. Whoops. I'm having trouble writing here. Infinite It is an infinite propagation speed of the singularities. In other words, we have a singularity at 0, it spreads out infinitely fast, it sort of collapses infinitely fast to the entire real line. Okay, this is going to be different. This is going to be true for diffusion and Laplace equations. Well, actually, Laplace equations is not really right to say that. It's going to be true for diffusion equations. Something somewhat similar is true for Laplace equations, but there's no time in Laplace equations, which is why I changed what I said. But for the time-dependent differential equations, the diffusion equation and the wave equation, and we'll look at the transport equation. For the transport and wave equation, it does not have this property here, this infinite propagation of singularities, but the diffusion equation does. And even though, let me just explain why, even though this is not mathematically true, let me explain like one of the sort of physical things that it kind of does reflect. Let's look at the following scenario. Let's say that we begin with a pipe like this. Think about, just imagine it as a finite length pipe, and we put some dye. There's like a very high concentration of dye right here. Obviously not infinite, but a very high concentration of dye right there, and it's zero everywhere else. Now after a day, we're going to have something. This is the same pipe, and now it's going to be spread out all throughout the pipe. It's going to obviously much more dilute than I've drawn here. The color dilution is not to scale. It's going to be spread out. Okay, now imagine a similar another experiment happening at the same time. Let's say instead of starting the dye here, you start the concentration here, and then after 24 hours, what are we going to have? Well, it's probably going to be so spread out that it's going to look almost exactly the same. So these will look almost nearly the same. Okay, now, according to the math, they're not going to be exactly the same, but according to physical intuition and really the math, they're going to be very close to each other. Whether you start the dye here or there, they're going to be very close to each other. Okay, so why is this important? Well, there's something called the backwards heat equation, which says let's start with this and run the heat equation in reverse and come back to the starting position. According to the mathematics, when you start with something like this, you're going to get exactly what when you look at this as the 24-hour later thing. If you run this in reverse, the math says you're only going to recover one initial condition, and it's this condition. And similarly, when you start from here, you're only going to cover one initial condition, and it's this condition. Okay, physically though, these are going to look almost identical. Maybe even according, by your equipment's precision, you're not going to be able to discern a difference. So what has happened is that it has the diffusion equation has so thoroughly mixed and so thoroughly diffused this, or I guess the diffusion equation models something that's being so thoroughly diffused that you can't really distinguish the after picture when you can clearly distinguish the before picture. Okay, and so this is one of the things that infinite propagation speed is kind of trying to capture, or not trying to capture, that it does capture. It's technically not correct, but at a slower speed, it kind of is true in the sense that we have two things that are virtually indistinguishable from each other, even though they are very different, even though they come from things that are very different. Okay, and this is why solving the backwards heat equation, you can look that up. I'm not going to talk about it much in these videos. Ask about it on the discussion forum, talk about it on the discussion forum. Solving the backwards heat equation is very difficult. My colleague, Dr. Peter Kuchman, says it like this: if you go into a bathroom and you go into a bathroom and people have been smoking and you see the cloud of smoke, it's very difficult to tell which stall the smoke was coming from. Okay, anyways, that's it.